about what you're going to write. So for the term paper, so I will make some suggestion and return to you individually in about a week or so that maybe people can focus on certain aspect of what you think you're going to write about this about the term paper. So I'll get that back to you soon. You have a term paper. You have a sort of assignment that was on the web, right? I think you have an assignment on the web, so you should take a look at that. You should be able to do it very soon, probably after this week or so. Let me see how I can turn on the lights here. People don't fall asleep. Okay, so today we're going to talk a little bit more about this surface crystallography, and let me just go back briefly about what we have said before. Today what we'll do is to try to cover surface crystallography and then maybe introduce the idea of electron diffraction, about trying to determine the surface structure of the surface itself. So let me just go back briefly where we were last day on this surface. So we have been talking about ideal surface at the moment, in the sense that we consider, you can think of ideal surface, if you don't have any absorbent on top of your surface, then the ideal surface is not the self-edge itself, it's sort of the top layer of the substrate just below the self-edge, because that's sort of like you still have three dimensions, including depth direction. The top skin is the ideal surface, because that's the surface, that's the layer without any reconstruction. Whereas if you go up higher into the self-edge, layer, then you will be talking about not the ideal surface anymore, because the layer could change. So let me try to clarify this. So we have, as I said before, we have this layer, right? So this is sort of usually there are two or three, let me draw three, and then down below you have this layer here, the spacing here is fixed, right? But then as you go into the self-edge region, the depth direction of these things may change. So these D's here may change. So this is what we know by the self-edge region, right? Self-edge region, and this below here is what we call substrate. So this is our definition for clean surface. Okay. So from this point on, you will not know any difference. This is a 3D symmetry, right? Both the depth direction. In here, the self-edge region, that's the 2D symmetry. So when we're talking about ideal surface, we are really talking about here, right? This layer, because really this layer is the one without any reconstruction. The atom does not move or anything like this, right? So on top here, the atoms are moving about due to reconstruction. So you cannot talk so much about that anymore. So the strategy here is to first explain the ideal surface first, and then try to deal with reconstruction, the movement from the ideal surface that you have. Okay, so that's the logistic. Now we are talking about here clean surface. In other words, there's no absorbate on top, and later on right? When we are talking about absorbate, when we have absorbate on top, then the jargon become even more confusing, is because when you're talking about the substrate at that point, you now include everything. So if you have an absorbate so this is for clean surface, right? If you are talking about absorbate, right, absorbate on top of this cell edge, then everything here from the cell edge and down is then called substrate. Okay, so this is for clean, this is for substrate. So let me, so there's a little bit of confusion, but in the literature, that's how people refer to it. In the literature, once you talking about a substrate, if you put stuff on the substrate, that means you have absorbate, then you include the cell edge region, and that whole thing becomes the substrate. But if you are talking about clean surface, then the substrate really is just below the cell edge region. Okay, so that's how we think about this. Okay, so yeah, so that's clear a little bit, and then so what we want to do is to first talk about the ideal surface here, the blue layer, if you like first, and then talk about how we learn about this blue layer. So we're talking about clean surface altogether so far, no absorbing yet. Okay, so we used the TLK model last time. We introduced this idea of TLK models, and we stand for terrace, ledge, and kinks, right? So we have terrace, we have ledge, which is the long thing here, the monoatomic step, a few atoms or one or two atoms, and then you have kinks, which are the defects along this line, this step lines that you have. Okay, and of course on the terrace there could be defects as well. You could have extra atom on top, or you could have missing atom on top, so-called vacancy defect. This is known as the atom defects. Those are jargons that people use. Okay, and we look at these structure. We talk about this roughness. They are singular surface, Messino surface. We talk about rough surfaces that you can obtain by just starting with a surface and just annealing it. You have the roughening effects as you go up in high temperature, and you can see this is a step surface, and we'll talk a little bit about that today. And going to roughened surface, you just need to anneal the temperature and anneal the substrate, and then you can sort of move around, and then you roughen the surface like this. We start looking at these crystallography last time, and we said that there are two dimensions, and let me just jump quickly. We talk about symmetry operation. There are 7 symmetry operations. Identity and 4 of the rotation, 2-fold, 3-fold, 4.5, 6-fold, no 5-fold symmetry. Nature doesn't like 5-fold symmetry. And then you have mirror refraction and blind refraction. So these are the sort of what you see on here. This is represented by different way of operating on one of the point in rotation. So for example, this one is rotation by 2-fold rotation, rotation by 180 degree. This is 3-fold rotation, rotation by 120 degree, and this is rotation by 90 degree, and so forth. Okay, and we introduced also last day about this idea of Buffet's lattice, just like crystallography, 3D crystallography that we talk about, Buffet lattice, and in the case of surface crystallography, there's only 5, and they are